Anyone who has ever managed like enterprise infrastructure knows the absolute dread of a maintenance window gone wrong.
Oh, yeah. It is a very specific kind of nightmare.
Right. I mean, you have the weekend, the users are offline, and you're executing this heavily planned server upgrade.
You're just watching that progress bar.
Exactly. You are watching the console, the installer hits, 99%, and you start thinking about finally going to sleep.
And then it just stops.
It hangs, yeah. A core service silently fails, the application locks up, and suddenly you are staring down the barrel of a multi-day outage for a mission-critical system.
The absolute worst feeling in IT.
It really is.
Yeah.
And today, we are taking you directly into the trenches of one of those exact scenarios. If you love peeking into the hidden architecture that keeps the modern business world running and analyzing the deep, granular mechanics of how things are fixed when they spectacularly break well, this deep dive is definitely for you. We are analyzing a fascinating postmortem from an IT managed services and repair company based in Oahu, Hawaii. They're called Cowabunga Computers. And we're working from this detailed breakdown written by a systems engineer who posts under the handle R0T.
Which is such a great handle, by the way, but we so rarely get to see this level of unvarnished technical reality.
Yeah, that's true.
I mean, we constantly hear marketing language about seamless cloud deployments and, frictionless updates. But at the operating system level, enterprise IT is still heavily reliant on deep systemic mechanics. The margin for error is just incredibly thin.
It really is. So our mission today is to explore how a microscopic, completely localized corruption in a background Windows process managed to bring a massive enterprise-wide database upgrade to a screeching halt.
It's wild how one tiny thing can just cascade.
Yeah. And we are going to break down the out-of-the-box, highly unconventional systems engineering it took to salvage the deployment. So, okay, let's unpack this.
Let's do it.
The environment belongs to a local Oahu construction contractor. And the project is a major backbone upgrade for their ERP software, Sage Timberline, which is currently known as Sage 300 Construction and Real Estate.
Right. And what's fascinating here is that this isn't just, a localized glitch on a single workstation.
No.
It's an absolute masterclass in hidden service dependencies and OS-level troubleshooting under severe time constraints. We really have to look at the architecture of Sage Timberline to understand the blast radius of this problem.
Yeah, because it's not a small piece of software.
Not at all. In the construction industry, this software is the absolute core of the operation. It handles highly complex job costing, which means pulling massive relational data from payroll, subcontractor invoices, materials.
Oh, it's just to generate those work-in-progress reports.
Exactly. It manages accounts payable and overarching project management. So, if the Sage server is down, the company cannot issue checks.
Right.
They cannot track site expenses. The business is effectively paralyzed.
So the stakes are incredibly high here. And the Cowabunga team, they approach the preparation with that exact mindset. Upgrading a legacy ERP like Sage isn't just a matter of running an executable and clicking next a few times.
If only it were that easy.
Right. You are talking about intense database schema conversions, updating client applications across dozens of workstations, and validating deep configuration metrics. The team spent hours just on the prep work alone.
Yeah, the prep is crucial.
They manually adjusted the primary backup schedules to ensure a fresh, pre-upgrade dataset was totally secured.
Good call.
And they actively verified the checksums and the completion logs of those backups. Then they utilized the hypervisor to create a server checkpoint.
Which is standard, but so important. A server checkpoint, whether you are using Hyper-V or VMware, is basically a hypervisor-level snapshot.
Okay, tell us more about that.
It captures the exact state of the virtual machine's disk, the system memory, and the hardware configuration at that specific second. Yeah, it creates a delta disk, meaning any new changes made during the upgrade are just written to a separate file.
I always look at that checkpoint like a save state in a video game.
That's a perfect analogy, actually.
Right. Like if you walk into a boss fight and everything goes terribly wrong, you just reload the save state. And suddenly you are standing right back outside the door with full health and all your inventory intact.
Yep, safe and sound.
Which actually brings up a crucial point I want to push on here.
Okay.
If the Cowabunga team had this pristine hypervisor snapshot, right, and they had fully verified offsite backups, why would a mid-upgrade crash cause a panic?
That is the big question.
If the software installer hangs and corrupts the database, couldn't they just restore the virtual machine from the checkpoint effectively hitting undo, and then try the upgrade again?
Well, reloading that save state guarantees you haven't lost your historical data, which is obviously vital.
Sure, you need the data.
But a rollback does absolutely nothing to resolve the systemic environmental trigger that caused the failure in the first place.
Oh, I see.
Right. If you restore the VM checkpoint and execute the Sage installer a second time, you are going to encounter the exact same unhandled exception at the exact same moment.
Because the problem wasn't the installer.
Exactly. The checkpoint preserves the pristine database, but it also perfectly preserves the hidden underlying OS corruption that's just waiting to be tripped by the installer.
So you avoid data loss, but you are still fundamentally stuck.
You are. You cannot complete the deployment until you identify the actual mechanism of the failure.
Wow. So the rollback saves the data, but the landmine is still buried in the exact same spot.
That's a great way to put it.
You still have to figure out how to defuse it. And for the Cowabunga team, that landmine detonated halfway through the server-side installation.
Right in the middle of it.
The upgrade process was progressing totally smoothly until the server's print Spooler service abruptly crashed.
Which sounds so random.
It does. It wasn't the Sage software itself throwing an internal database error. It was the Windows Server operating system failing underneath it.
And anyone managing Windows Server environments knows the print spooler is notoriously fragile.
Oh, yeah.
But we need to look at why a failing print spooler is such a catastrophic event for a financial application like Sage Timberline.
And here's where it gets really interesting. Because you might assume that if the print service dies, you just, I don't know, can't output physical paper for a while.
Right. You think, oh, I'll just print it later.
Yeah. You finish the ERP upgrade, you let the database conversions run, and you just fix the printer connection on Monday morning.
But that's not how it works here.
Right. So why did a spooler crash completely hang the entire Sage installation process? Like, I think of the print spooler as just the thing that talks to the printer.
Yeah, it comes down to how legacy enterprise applications handle dynamic report generation. Sage Timberline doesn't just send raw text to a physical printer.
Okay.
Its internal reporting engine relies heavily on the Windows Print Spooler API to render forms, to calculate page metrics, determine margins, and generate print previews on the fly.
Wait, so it needs the spooler just to build the preview?
Exactly.
That's right.
When the Sage installer or the core application tries to initialize its reporting modules, it makes what's called an RPC call, a remote procedure call to the spooler service.
Got it.
If the spooler is dead, that RPC call times out.
Oh, no.
Yeah. The application thread receives no response, it throws an unhandled exception, and the entire core processing loop locks up.
So it's like the starter motor in a car. You can have a brand new engine, the upgraded software, but if the starter motor is busted, you aren't going anywhere.
That is perfectly said. The software becomes functionally useless because the reporting engine is hard-coded into the daily workflow. It's friction between the application layer and the OS layer.
The application layer is demanding a service that the OS layer simply cannot provide. So the Cowabunga team sees this spoolsv.exe process terminating unexpectedly.
Just dying on them.
Yeah, it attempts to start, runs for a fraction of a second, and just dies. So they immediately dive into standard OS-level troubleshooting. They stop the service and clear out that printer's directory, the one in System 32.
Right. See Windows System 32 spool printers. Standard move.
Right. They assume a stuck spool file is causing a buffer overflow. They try manually forcing the service to restart via the command line. They even attempt to strip out the third-party printer drivers from the environment.
And let me guess, none of it works.
None of it works. The service continually crashes because the actual Windows registry entries governing the print subsystem are deeply, fundamentally corrupted.
Wow. And the registry is essentially the central configuration database for Windows.
Yeah, it's the brain.
It dictates how the kernel interacts with hardware, how services initialize, and where the OS actually locates the physical binary files it needs to execute.
Right.
So when the registry paths tied to the spooler service become corrupted, standard application-level fixes are totally irrelevant.
Because the foundation is broken.
Exactly. The OS is essentially reading scrambled routing instructions.
I always think of the Windows registry like a massive, complex catalog of GPS coordinates for the operating system.
You know, I like that.
Right. When Sage asks Windows to handle a print job, Windows looks up the GPS coordinates in the registry to find the exact DLL files and driver configurations needed to execute that request.
Precisely.
But if those coordinates are corrupted, the request just drops into a black hole and the service crashes.
And at this point in the maintenance window, the IT team is trapped.
Completely trapped,
Right.
because you cannot easily reinstall Windows Server in the middle of an ERP upgrade.
Oh, absolutely not.
Right, you'd be throwing away massive amounts of configuration work and risking the integrity of the whole environment.
Yeah, you are dealing with an environment that likely has custom domain policies, really complex network configurations, and intricate security permissions already established.
You can't just wipe all that.
No, flattening the OS and starting over is the absolute nuclear option. It guarantees a massive delay for the client.
Which forces the team into some extreme, entirely non-standard systems engineering.
This is where it gets really crazy.
Yeah. The on-site engineer brings in another member of the Cowabunga team just to get a fresh set of eyes on this failing server.
Always a good idea when you're stuck.
And they quickly realize that manually identifying and correcting every single corrupted string within the registry hive is practically impossible.
You'd be there for weeks.
You don't know how deep the corruption goes.
So,
They pivot. They locate a completely separate, healthy machine running Windows Server 2019 that has a stable, heavily tested print spooler configuration.
okay, I see where this is going.
They decide to extract the registry keys from the healthy server and surgically graft them into the corrupted production server.
Wow. That represents a massive escalation in troubleshooting.
It's like an organ transplant.
It really is. Modifying the registry of a live production server is inherently dangerous. Extracting entire subkeys from a different machine and merging them into a new environment requires a microscopic understanding of how Windows handles the service dependencies.
Because they are essentially performing a routing table transplant.
Yes.
They go into the healthy server 2019 machine, and they export the specific registry paths, probably targeting the spooler directory under current control set, along with all the associated print monitor and provider keys.
Just pulling the raw .reg files.
Exactly. They save those out as raw files, pull that digital architecture over to the corrupted Sage server, and import it directly. They overwrite the damaged entries to provide the spooler service with a fresh foundation.
It's a bold move.
And I actually have to push back on this approach because that sounds incredibly risky.
This raises an important question, yes.
Right. If the registry is governing driver loads and hardware interaction, how do they know pasting in foreign registry keys won't trigger a system-wide rejection? Like, couldn't bringing over configuration data from a completely different machine cause a fatal conflict?
Like a blue screen of death.
Yeah, exactly. Couldn't it completely brick the target server?
Well, the risk of a fatal conflict is exactly why this isn't a standard operating procedure. If you were to copy the entire current control set, or just blindly overwrite hardware-specific enumeration keys, you would absolutely crash the kernel.
Right, because the hardware doesn't match.
Exactly. The target server would try to load storage controllers or network interfaces that don't physically exist on that machine.
And then boom, immediate blue screen.
Boom. So to answer your question on how they execute the merge safely, how they avoid taking down the whole server, it's all about isolating the exact boundaries of the subsystem.
Okay, explain that.
The Cowabunga engineers didn't just copy random registry data, they identified the precise structural keys that dictate the default behavior of the native Windows print spooler.
Independent of the drivers.
Entirely independent of the specific hardware drivers. They know that the base configuration for spoolsSV.exe on Windows Server 2019 is heavily standardized.
Yeah, I see.
By exporting only those highly specific isolated keys, they ensure they are only overwriting the corrupted logic governing the print service itself. They aren't touching the keys that control the hypervisor tools, or the network stack, or the storage array.
So it requires this really intimate knowledge of what data is actually contained inside those registry paths.
Intimate is the word.
You have to know that the keys you are merging don't contain environment-specific variables.
Like a hard-coded local IP address?
Right. Or a unique machine identifier that will certainly conflict with the target server. You have to ensure the physical binary files referenced in those keys actually exist in the System32 directory of the SIC machine.
And you also have to navigate Windows security protocols, which is no small feat.
Oh, right. Permissions.
Yeah, by default, critical registry keys are owned by the trusted installer security principal. To overwrite them, the engineers likely had to forcefully take ownership of the corrupted keys.
Just to get access.
Right. They grant themselves full control permissions, execute the merge of the registry files from the command line, and then verify the file system integrity. It is an incredibly precise operation.
And the precision totally paid off immediately. After they imported the fresh foundation from the healthy server, they went into the services console and fired up the print spooler.
Ah,
It started cleanly.
amazing.
The process stayed running without terminating. They ran a series of print tests directly from the OS and then pushed test reports through multiple different applications
Hmm.
just to validate the stability of those RPC calls.
You have to be sure it's actually stable.
Right. And everything processed flawlessly. The underlying OS routing was restored, which meant the Sage application layer could finally communicate with the Spooler API again.
Which is huge. Stabilizing the operating system foundation allows the actual objective of the maintenance window to resume.
Yes.
The Print Spooler crash was a massive detour, but once it was resolved, the deployment process had to continue.
Right back to the ERP upgrade. So the Sage consultant, who, by the way, was managing the application layer and is a separate entity from the Cowabunga OS team, they were finally able to step back in.
That separation of roles is highly typical in complex enterprise deployments, actually.
Right.
Yeah, you have application specialists who possess deep knowledge of the software's internal database structure. And then you have systems engineers who maintain the integrity of the underlying virtual machines and the OS.
That makes sense.
So when the OS fails, the application specialist is completely blocked until the systems engineer can restore the environment. They literally can't do their job.
Well, with the OS stable, the consultant completed the massive database schema conversions that had been totally stalled. And once the server-side databases were fully upgraded, the team pushed the new Sage 300 CRE client software out to the various user workstations across the office.
Nice. And they test the user logins across the network, right?
Yep, verifying that the client applications can successfully query the newly upgraded database without throwing any connection errors. And the Cowabunga team highlights a really critical final step in their post-mortem here.
What was that?
Before signing off on the project, they initiate a full restart of all the office workstations and, most importantly, a clean power cycle of the Sage Timberline server itself.
Yes, a clean boot.
Yeah.
That is the ultimate validation of a registry-level fix. You absolutely have to prove that the manually injected registry keys are persistent.
Exactly. You have to ensure that when Windows shuts down and rebuilds its hardware abstraction layer on the next boot, the Spooler service still initializes correctly using those transplanted keys.
Because if the fix only works until the server is rebooted,
You haven't actually fixed the problem.
no, you've just delayed the outage until the next Patch Tuesday.
Right. But once the entire environment came back online cleanly, they walked the client's internal team through the new installation process, empowering them to manage any straggling workstations the following morning.
A total success.
So what does this all mean? Why did we spend this deep dive analyzing the granular mechanics of a broken print spooler in a Hawaiian construction firm?
It's a great question.
The core takeaway from Cowabunga Computers is a stark reality check regarding enterprise infrastructure.
It really is.
Regardless of whether you are deploying Sage Timberline, highly customized SQL clusters, or legacy ERP systems, the upgrades carry profound risk.
And that risk rarely stems from the software installer itself.
No, it stems from the hidden, microscopic corruptions and environmental anomalies buried deep within your operating system. Issues that remain completely invisible until the exact moment an upgrade relies on them.
If we connect this to the bigger picture, it fundamentally challenges the way we view modern IT deployments.
How so?
Well, we have been conditioned by the mobile app ecosystem and cloud platforms to view upgrades as automated, frictionless events.
Right. Update app. Done.
Exactly. You click a button, a container is spun up, and the new version is deployed. But underneath that abstracted application layer, enterprise software still relies on incredibly complex, deeply layered OS architecture.
You can write the most elegant application code in the world, but if the OS fails to route a service call, the application crashes.
And automation cannot solve foundational OS corruption.
No script is fixing that registry.
Right. You cannot write an installation script that anticipates and automatically untangles every possible manifestation of registry decay. When the underlying architecture fractures, it requires engineers who possess human ingenuity, deep critical thinking, and an intimate understanding of operating system mechanics to manually intervene.
Because if your IT strategy only involves engineers who know how to manage the application layer or, just click through a graphical interface, an OS-level failure will result in an unrecoverable maintenance window.
Absolutely. The checkpoint will save your data, like we discussed, but it won't get the system back online.
You need systems engineers who understand how to operate outside the standard checklist. The Cowabunga team succeeded because they understood the structural boundaries of the Windows OS well enough to perform a live registral transplant without crashing the kernel.
It really is a remarkable example of technical problem solving under pressure.
It's amazing. So to quickly recap our deep dive today, we examined a highly prepped Sage Timberline ERP upgrade for an Oahu contractor. We had verified backups, pristine hypervisor checkpoints,
All the right prep.
but the deployment hits a massive wall when a corrupted registry tree causes the Windows print spooler to endlessly crash, which of course locks up the application's reporting engine.
And standard OS troubleshooting fails completely.
Right. So ultimately, the engineers salvaged the maintenance window by carefully extracting the specific print subsystem registry keys from a healthy server 2019 machine and surgically merging them into the corrupted production server, restoring the OS foundation and allowing the database conversions to finish.
It's brilliant. But, it leaves me with a lingering thought that I think you, the listener, should deeply consider as you look at the future of your own IT environments.
Oh, I always appreciate these. What is the final thought for today?
As our infrastructure becomes increasingly dominated by cloud abstraction, as we move further into platform as a service models and serverless environments, are we slowly losing the fundamental mechanic skills required to lift the hood and troubleshoot the underlying OS engine?
Oh, wow.
We are currently training an entire generation of IT professionals to manage applications exclusively through web dashboards and automated deployment pipelines, but the physical plumbing still exists.
It's still there underneath.
Exactly. When that foundational operating system inevitably stumbles and the abstraction layer fails, who is going to possess the granular knowledge required to perform a registry transplant?
That is a scary thought.
Right. 10 years from now, who is going to understand the system architecture well enough to actually save the patient?
That is a phenomenal question. As the technology becomes easier to deploy from a dashboard, the underlying mechanics kind of become a lost art.
Exactly.
Well, that is all the time we have for today. Thank you so much for joining us on this deep dive into the hidden complexities of enterprise server upgrades and registry mechanics. Keep looking behind the curtain, keep analyzing how your infrastructure actually functions at the OS level, and keep questioning the invisible dependencies you rely on every single day.
Because as we saw today, a massive enterprise deployment can be entirely derailed by a single corrupted routing instruction.
It sure can. We will catch you next time.